Somewhere over your head, right this moment, is an artificial satellite. Many of them, actually. They beam television and radio signals down to Earth. They can tell us our exact time and location, and they can also help us predict the weather. And they're now even being used to provide broadband internet. But how exactly do they work? How do you get something to whiz around in space without crashing down? Learn more about how satellites work, as well as some of the misconceptions people have about them, on this episode of Everything Everywhere Daily. This episode is sponsored by the Tourist Office of Spain. The global pandemic has obviously had a huge impact on travel over the last year and a half. Even though things are now opening up, every country has different rules and regulations for every other country, which can make traveling really confusing. That's why Spain has created a portal to help you know what you need to do in order to visit Spain. Just go to travelsafe.spain.info and get all the information you need to plan your trip to Spain safely and securely, with information tailored for your country of origin. It will tell you the latest up-to-date information for traveling from your particular country to Spain, as well as answering all of your common questions about when you're there and when you'll return home. I know many of you, like myself, are thinking of returning to Spain as soon as possible, so you owe it to yourself to check out the website before you go. Once again, that's travelsafe.spain.info, or just click on the link in the show notes. Unless there are some astronauts in the audience, all of us have used the surface of the Earth as our frame of reference for our entire lives. For example, if I have a ball and I want you to have the ball, I would throw the ball directly to you. Very simple, and everyone understands that. When you start talking about things in orbit, however, they can often be mind-bendingly confusing. Things that seem like they would be obvious are not in fact at all obvious. Let's start with one of the biggest misconceptions people have about how satellites get to orbit. They think that they get there by going really high above the surface of the Earth. This is in fact not true. Yes, satellites are high above the Earth, but that's because that's where we have to go to get away from the atmosphere. Let's conduct a thought experiment. Let's say that you have a really big rocket and that it's in your front yard. You're going to launch this rocket straight up into the sky. And by straight up, I mean straight up. At every moment the rocket is above you, its initial launch point is directly below it. Now let's say that we take it all the way up to the same altitude as the International Space Station, which is about 420 kilometers or 260 miles above the Earth. Now let's also say that we have really good timing, and we timed it such that the rocket will be in the same spot as the International Space Station at the same time. Could your rocket dock with the space station? And the answer is emphatically no. If anything, it would cause a massive disaster, because the ISS would smash into your rocket at a speed of 17,000 miles per hour. The problem is your rocket isn't in orbit. It's just at a very high altitude. Once it runs out of fuel, it's going to fall right back down to Earth, even though it's at an altitude where satellites are orbiting. Getting into orbit is not about altitude. It's about velocity. When we see a rocket launch, it does go straight up, at least at first. However, it will eventually begin to arc and put most of its energy into moving laterally, not vertically. The problem is, by the time it's doing that, it's far enough away that we can't see it. The first person to figure out that an orbiting gravitational body was possible was Sir Isaac Newton. He imagined the problem as a giant cannon, because he didn't have rockets back then. According to Newton, suppose you had a cannon on the top of a tall hill and you fired it. The cannonball would arc through the air and land. Now suppose you kept firing progressively more powerful cannonballs. They would be launched from the cannon faster and go further. Eventually, they would land beyond the horizon as the Earth is curving. You might even be able to fire a cannonball powerful enough to send it around the Earth, which would hit you in the back, assuming that you fired it in the right direction. However, if you fire a cannonball powerful enough, it will keep flying around the Earth and missing it. It will literally be falling around the Earth. The speed at which this is achieved for the Earth is 11.19 kilometers per second. The speed at which this happens is known as escape velocity, and that's why astronauts are often said to be in free fall. They are technically in zero gravity. It's the gravity of the Earth that keeps them falling. Airplanes that can do steep dives can experience several seconds of free fall, and passengers can have that same sensation that they do in space. Douglas Adams wrote in The Hitchhiker's Guide to the Galaxy that flying was throwing yourself at the ground and missing. Replace flying with orbiting, and he basically got it right. Now let's assume that you are in space, and you're working on the space station, and you're working outside the space station in your spacesuit, and you're staring at the Earth as it goes by. On a whim, you decide to take the wrench that you have in your hand and throw it directly down at the surface of the Earth. What will happen to the wrench? Now, the obvious answer that most people would give is that the wrench would keep going towards the Earth, and it eventually would burn up in the atmosphere as it heads towards the Earth. That is not what will happen. All you've done is put the wrench into a different orbit. The new orbit will be more elliptical, and its closest point will be closer than the space station. But the farthest point in its orbit will actually be further away from the Earth than the space station. Even though you threw it towards the Earth, it will eventually be farther from the Earth from the point where you threw it. Now, the wrench will eventually enter the Earth's atmosphere and burn up, and it will do so faster than the space station will. That's because what matters is the perigee in its orbit, that being the closest point in its orbit. The perigee is where you experience the most atmospheric drag. This is why maneuvering in orbit is so complicated. It isn't at all as straightforward as going from point A to point B. When we fly probes to Mars, we don't just point a rocket at Mars and fire. If you look at the path the probe actually flies, it looks like a very elongated spiral. You can't just fly in a straight line to Mars for the same reason you can't just fly in a straight line to the International Space Station. One other orbital paradox has to do with the Sun. Many people often suggest things like we should launch all of our nuclear waste into the Sun. To be sure, launching anything into the Sun would get rid of it. However, that's very, very hard to do. Believe it or not, it's actually easier to launch something out of the solar system than it is to launch something into the Sun. That's because the Earth is moving around the Sun at a high velocity, 30 kilometers per second to be precise. To get to the Sun, you would have to negate all of the velocity of the orbit of the Earth, and that's almost 3 times greater than Earth's escape velocity. To make things even more confusing, it would be easier to launch something into the Sun from Pluto than it would be from the surface of Mercury. And it all has to do with the fact that Pluto travels much slower than Mercury. Whenever a satellite is put into orbit, it has certain properties. Altitude and velocity are 2 that I've just discussed. Another important one is its inclination. This is just how much the orbit of the satellite is tilted with respect to the equator. Very few satellites actually travel directly over the equator. Most are inclined somewhat. If you've ever seen a world wall map from a mission control room from a spaceflight, you'll notice that the lines on the map that follow the spaceship look like sine waves. This really is just the representation of the inclination of the satellite when put on a flat map. If you have a 90-degree inclination, then you have what's known as a polar orbit. Polar orbits are usually used for satellites that do Earth observation. This includes spy satellites, mapping satellites, and satellites that take all the photos that you see on Google Maps. Another important orbit are geosynchronous or geostationary orbits. Technically, they're different, but they're often used synonymously. The ISS takes about 90 minutes to orbit the Earth. As you go to a higher and higher orbit, that time takes longer and longer. Eventually, if you get high enough in altitude, to be precise, 35,786 kilometers, then the time it takes to orbit the Earth is exactly 1 Earth day. A geosynchronous orbit is any orbit of 1 day, regardless of its inclination. A geostationary orbit is a geosynchronous orbit that has 0 inclination. It's directly over the equator. Geostationary orbits are extremely useful. The idea for them was originally proposed by science fiction writer Arthur C. Clarke. If you have satellite TV, you are getting that signal from a satellite in geostationary orbit 22,236 miles away. You can actually tell the latitude of wherever you are in the world by looking at satellite dishes. Satellite dishes in Iceland, for example, are almost pointing at the horizon. Is there an equivalent to a geostationary orbit for polar orbits? The answer is no. Satellite communication for polar areas is extremely difficult. One solution the Soviets came up with was called a Molniya orbit. This is a highly elliptical orbit with the furthest point from the Earth above the Arctic and the closest point over the Antarctic. Most of the time, the satellite will be over the Arctic, but it will be out of view briefly as it passes around the south. In order to have continuous coverage, you need to have several satellites to be operating at once. The final thing I'll mention are special points in orbit when you have two large objects. In the case of the Earth and the Moon, for example, there are 5 points known as Lagrange points, where the gravity of both bodies are balanced. These points were named after 18th century French mathematician Joseph Louis Lagrange, who came up with the idea. The 5 points are known as L1, L2, L3, L4, and L5. I mention this because the next big space telescope that is scheduled to be launched in November 2021 will not be in orbit around the Earth like the Hubble telescope is. It will sit at L2, which is the point beyond the Moon. In fact, it will be located 1.5 million kilometers away from Earth at a point where it will always have a view of the dark side of the Moon. The James Webb Telescope is an incredible piece of equipment, and the program is really amazing, and I'll probably be doing an episode on it as the launch date gets closer. So if you've ever wondered why rocket science is used as a metaphor for something that's really hard, I think you can now see why. Getting to orbit and moving around in orbit is really challenging, and it doesn't at all make any sense based on what we know from living on Earth. The associate producer of Everything Everywhere Daily is Thor Thomsen. If you'd like to support the show, please donate over at patreon.com. There is content only available to supporters, merchandise, and even opportunities for a show producer credit. If you know someone you think would enjoy the show, please share it with them. Also remember, if you leave a 5-star review, I'll read your review on the show.